How do you ensure robustness in feedback control systems? Imagine trying to steer a boat through choppy waters. You want it to stay on course even when waves and wind push against it. That's what robustness in feedback control systems is all about. It's about making sure your system keeps working well, even when things don't go exactly as planned. In electrical engineering, this means designing control systems that stay stable and perform reliably despite uncertainties and disturbances. First, understanding what robustness really means is key. It's about how little a system's performance changes when the actual system, called the plant, differs from its mathematical model. Variations in components, external disturbances, sensor noise, or unmodeled dynamics can all throw things off. A robust system can handle these issues without losing stability or becoming unpredictable. Feedback control is the backbone here. It works by constantly comparing the output to the desired reference. If something drifts or noise appears, the controller adjusts the input to correct it. This continuous correction helps reduce steady errors and improves how quickly the system responds to changes. It also helps reject disturbances, making the system more reliable. Designing for robustness involves explicitly considering uncertainties. Engineers model possible variations and disturbances during the design process. This way, they can create controllers that keep the system stable across a range of conditions. For example, they might include safety margins in gain and phase to prevent instability if parameters shift or delays happen. Modern techniques like H-infinity loop shaping are used. This method adjusts the open-loop frequency response to balance performance with robustness. It shapes how the system reacts at different frequencies to ensure it can handle worst-case uncertainties. Loop transfer function shaping is another approach, where the frequency response is tuned using Bode plots to meet gain and phase margin requirements. Structured singular value analysis measures how much uncertainty a system can tolerate before it becomes unstable, giving a clear picture of robustness. But there's always a trade-off. Making a system more robust can sometimes slow down its response or reduce accuracy. Engineers must find the right balance based on what the system needs most. Practical considerations also matter. Using sensors and actuators with enough bandwidth, avoiding delays in feedback paths, and filtering noise are all important steps. Testing the system under different conditions helps verify it can handle real-world variations. In electrical engineering, these principles are applied everywhere. Power systems use robust feedback to keep voltage and frequency steady despite load changes. Motor drives and robots relying on it for precise motion control even when loads vary or mechanical parts wear out. In communication systems, feedback reduces distortion and noise, ensuring clear signals. By combining these strategies, engineers create feedback control systems that stay stable and effective no matter what real-world conditions throw at them. That's how robustness keeps systems reliable, safe, and ready to perform in everyday life.